The TF-IDF algorithm assigns a numeric weight, that is a number, to every word in the corpus. How is the number which represents a particular word calculated? We'll start off by looking at the one hot method of representing text in numeric form. Let's say that we wanted to perform sentiment analysis of movie reviews. Now, this reviews database could be part of IMDb, Rotten Tomatoes, or any other movie review site. Each review is considered to be one document, and the set of all reviews that is available on this site is our corpus. So let's imagine that the capital D represents the entire corpus, and D of I is one document in that corpus. That is a single review, whether positive or negative. In order to represent the words that make up this review in one hot notation, which is a numeric representation of the word, we would split up the entire corpus into individual words. We'll create a set of all words, unique words, across the corpus. If a word appears more than once, it's present just once. Remember, this is a set of words. This set of words forms our vocabulary. This term vocabulary only refers to the words that are actually present in the reviews. It doesn't refer to English vocabulary as a whole. Once we have an ordered list of all the words that have ever been seen within the reviews on our movie database, you can express every review as a tuple of 1 0 elements. Let's say the review comprised of a single word which just said amazing. You would have the element 1 at the position of amazing in your ordered list. The remaining elements would be 0. If the review said worst movie ever, then you would have the element 1 at the position of worst movie and ever, and the remaining elements would be 0. 1 indicates that that word is present in this review. You'd basically use this representation and apply it to every review that you have in your database. The number 1 to represent that the word exists in your review, the number 0 to indicate that the word is not present in your review. Every tuple of 1 0 elements that you generate in this way will have the number of fields equal to the vocabulary of your dataset. At the end of this process, all of your reviews have now been represented using one hot notation. Notice that individual words do not have a numeric representation, but sequences of words do. They are represented by using the number 1 for a word that is present within a review and the number 0 for a word that is not present. This one hot representation forms the feature vector that is the input to our machine learning model, and the length of this feature vector is equal to the size of our vocabulary. The cool thing about using one hot encoding in order to represent your reviews is the fact that we can compare the distance between reviews using simple geometry. You'll find that reviews which express the same sentiment, for example, negative reviews, will have a lot of words in common, such as worst, I hated it, it was boring, and so on. Now, when you compare the distance between the reviews, you'll find that negative reviews will tend to be closer together. The same thing is true for words which appear in positive reviews. You will find one hot notation has its advantages, one of which is that it's simple and you can measure distance between reviews using simple geometry. However, there are several flaws which make one hot encoding not our encoding of choice. The first is that if you have a very large vocabulary, if you have a database with a lot of reviews, which means the vocabulary will be large, the feature vectors will be enormous. Remember, every review has to be expressed in terms of all words which exist in the vocabulary. The second flaw is the fact that you actually lose important information when you represent reviews using one hot notation. You have no idea of the order in which the words occurred in the original review. You have information about whether a word occurred in the original review or not, but you have no idea where in the sequence that word actually was placed. One hot notation shows us only the existence or non existence of a word in the review. You've no idea whether the word occurred more than once. Let's say you really loved the movie. A review might be loved, loved, loved it, which is a much stronger positive review than simply saying, I love the movie. You don't have this frequency information of individual words. Let's now look at the second method we have for generating word encodings or representing words in numeric form, the TF-IDF, term frequency inverse document frequency. We've seen earlier in this lecture that we can represent a document as a tensor of numeric encodings. Here, x0 through xn are word encodings, and those words make up this single document. So, if this document was a review, this is not the worst restaurant in the metropolis, not by a long way. Each individual word in the review would be represented by some numeric encoding, and these numeric encodings come together to form the document tensor. When you use the TF-IDF algorithm, the numeric representation of every word will be the product of two terms. The two terms are the term frequency of the word and the inverse document frequency of the same word. In order to understand what these terms mean, let's go back to our corpus of reviews. Capital D represents the entire corpus, and D of I is one document in this corpus. One document is a single review. The TF-IDF algorithm tries to capture for every word the significance of that word within a single document, that is a single review, and the significance of the same word across the entire corpus of documents. That means the encoding of word I in some document J depends on that word itself, the document where it belongs, and also on the entire corpus. The TF-IDF is a multiplication of two terms. The term frequency of a word is a measure of how frequently the word I occurs in document J. The more frequently a word occurs, the higher this term frequency value will be. For example, if you say this was the worst movie, you know that the term frequency of the word worst for this particular review will be higher than if you just say this was the worst movie ever. The significance of the word worst when repeated three times is higher than if it was repeated just once within a review. The inverse document frequency tries to capture something different. This is a measure of how infrequently a word I occurs in the entire corpus D. A word is more significant when it appears within a particular review if it's infrequent across the corpus. Let's say a lot of positive reviews use the word amazing, then the significance of that word gets reduced because it occurs very often within the corpus. Then, when you have a word like stupendous, it holds much greater significance because it's rare across the corpus. The TF-IDF algorithm tries to capture the significance of both of these terms. It assigns a high weight for a word I in document J if the word occurs really frequently within this document but rarely elsewhere. This TF-IDF method is commonly used in search algorithms in order to assign weights to search terms. The TF-IDF method offers some important advantages over the one-hot representation that we saw earlier. The first thing is the feature vector is much more tractable in size. Since every word has its own numeric representation, the feature vector used to represent a single review can be at most the length of the longest review in our document corpus. The term frequency term in the TF-IDF method captures the frequency with which a word occurs within a particular review or a particular document. The relevance of that word is also captured using inverse document frequency. If a word is rarely used, it's more relevant. The TF-IDF method still has one big drawback. Every word is considered individually and it's not considered in the context of the words that surround it. The semantic relationship that exists between words in a single document is not captured. And this is where the third method of representing words in numeric form is so powerful. Word embeddings allow you to encode words such that their semantic relationships with other words and their meanings are captured as well. Word embeddings are generated using a machine learning model. This is typically an unsupervised learning model, which basically looks at patterns of words which it has been fed in the past. It is generally trained on a large corpus of data, such as Wikipedia or some such huge corpus of text data. Once this machine learning model has been fed in this huge corpus, it's ready to accept new words and spit out embeddings for those words. It'll accept a word such as London and generate a numeric embedding for it. Now, this numeric encoding, though, is special because it also captures the meaning of the word London somehow. By using the large corpus of data that we fed it, this ML based algorithm is able to understand that London references a city. So if you feed in words such as New York, Paris, which are also cities kind of like London, important global cities in the world, the encodings that this ML based algorithm will generate for these cities will be very close to the encoding of London. If you were to visualize these numeric encodings in some kind of graphical representation in n dimensional space, you'd find that encodings for these global cities are very close together. Encodings for similar words, let's say Monday, Tuesday, Wednesday, which are the names of days of the week, the encodings for those would be close together as well. Now, this sounds too good to be true. It sounds almost magical, but it works, provided the corpus of data is large enough in that it has many examples of words which are similar used in different contexts. Our machine learning algorithm is able to find these patterns of words which are similar to each other. The word London that we feed in is called the input word, and the resulting numeric representation of London is called the word encoding or embedding. One important feature of the word embedding that is generated in this manner is that it has a very low dimensionality. This low dimensionality embedding serves as a very compact representation of the word itself, the semantic relationship that this word has with other words, and the word's meaning. In order to get a good word embedding from your machine learning model, it's very important that it train on a very large data set. The corpus of data that you feed into this model is typically like all articles in Wikipedia or many, many books. The machine learning model has to have many examples of how the word is used in different contexts in order to establish the semantic relationships and the meaning of the word correctly. This machine learning model is typically an unsupervised learning algorithm. The training data set that you feed in is not labeled data, it's unlabeled data, and this neural network, that's what it usually is, finds patterns within this unlabeled data. These word embeddings are really kind of like magic because they capture meaning. And because these word representations are actually numbers, you can compute things with words which you didn't think were possible, things which are possible only mathematically, such as queen is equivalent to king plus woman minus man. You'll get an embedding which is close to the embedding of queen, or Paris is the equivalent of France plus London minus England. The word itself is represented with very low dimensionality. It's just a number rather than a long series of characters. In addition, computations on the number can yield surprising and interesting results that you can use in your other machine learning models. There are two popular algorithms which are used to generate these word embeddings. The first of these is called word to vec. This is the most popular word embedding model. There are two different implementations of the word to vec model. One is called the continuous bag of words, and the other is called the skipgram implementation. This algorithm was first developed by Mikolov from Google in the year 2013, and it basically uses an input word to predict the words that surround it, or uses the surrounding words to predict the input word. This is fed into a shallow or simple neural network, and this allows it to learn word embeddings. Another popular word embedding model is GLOVE, or Global Vectors for Word Representation. This was developed by PhD students at Stanford in the year 2014, and it does not use neural networks. Instead, it uses word to word co occurrence matrices and the nearest neighbors algorithms in order to extrapolate word relationships. Co occurrence matrices can be thought of as a window over the words in a text, which allow us to determine which words tend to occur together. TF-IDF stands for term frequency inverse document frequency. For any word in a particular document, the term frequency gives a higher weight to that word if it's present more often within that document. The inverse document frequency sees how rare that word is. It gives a higher weight to that word if it's rare in the entire corpus. It's not present very often in the entire corpus. The final weight assigned to a word is a multiplication of the term frequency and the inverse document frequency.